Hi, I'm Tim Pedersen from Aarhus University in Denmark. The motivation for doing this work is that we wish to find the best possible way of reducing emissions from our energy supply. To do that, we use energy system optimization models to look at possible future scenarios. The problem is that these energy systems, they are subject to some very complex political agendas. Because we are not always capturing this entire complexity in the model, it can be very relevant to look at solutions with other qualities than necessarily cost, as we usually do. Some of these qualities might be land use, transmission expansion, equality in the energy supply, or transition speed. State-of-the-art works use a method called modeling to generate alternatives to look at a few alternative scenarios. We wish to improve on that by modeling all the near optimal solutions. So first of all, the research question that we asked ourselves is, how do we do this? And secondly, what information does these near optimal solutions provide us? In this work, we have used a simplified version of our model of the European power sector. In this simplified version of our model, we have 3 energy generating technologies. These are namely solar PV, wind turbines, and open cycle gas turbines. We have also included 2 storage technologies. These are battery and hydrogen storage. We have enforced a 95% CO2 reduction constraint on the model to look at some highly decarbonized future scenarios. Input data for the model is hourly resolved weather and energy demand data. We have also included data for the network topology, technology costs, and some technical constraints. The model is then formulated using a series of linear constraints and a linear objective function. When applying an optimization algorithm to the model, we obtain some variable values for installed technology capacities, technology dispatch, and transmission line capacities. We can also evaluate our objective function to obtain the total system cost of our system. If we start by considering just 2 variables of our model, these could be the installed wind turbine capacity and the installed solar PV capacity. We can then represent all possible solutions to our model in this 2-dimensional graph. We could indicate the value of our objective function with these contours, increasing as we install more of these capacities. But as we wish to ensure realistic operation of our network, we enforce some technical constraints, limiting us from where we can be in this solution space. Usually what we do when we apply an optimization algorithm is to find the cost optimal solution. That is, the solution with the lowest total system cost. But what we are interested in this work is to look at solutions that are near the cost optimal solution in terms of total system cost, but has a different technology mix and therefore possess some other qualities than just having the lowest total system cost. These solutions are marked here with the blue region, and we refer to this group of solutions as the near optimal solution space. The concept of a near optimal solution space is rather abstract. Therefore, I will give a few examples of what these near optimal solutions could look like. So first of all, we have the cost optimal solution of the model, but we could also have something completely different, such as this scenario here, where we have a very high penetration of wind power, or we could have something like this, where we have a very high penetration of solar PV. We could also have something completely different, such as this scenario that we see here, where we have a very high equality in the model. And by equality, I mean that the countries are producing the majority of the energy that they consume. In order to identify all of these near optimal model solutions, we present the novel method titled Mapping All Alternatives. The method consists of a few steps that I will present here. So first we find the cost optimal solution of the model. We then introduce a new constraint into the model, limiting new solutions from increasing in total system cost to no more than the cost of the cost optimal solution plus some user specified amount of slack. We then maximize and minimize all the variables in the model to find a new set of alternative solutions. These solutions are indicated here with these small blue dots. Because we know this is a convex optimization problem, we identify the convex hull containing all known solutions so far. Then, by changing the objective function to be a multiple of one of these normal directions and the variables in the model, we can continue finding new solutions located beyond our known convex hull. Then, by repeating the process of identifying the convex hull containing all known solutions and searching for new solutions in the phase normal directions, we can continue expanding the convex hull that we know. And actually, if we keep track of the volume, we'll see that it converges towards the volume of the entire near-optimal model solution space. But what we are interested in is actually a dataset representing all the solutions inside of this convex hull. And fortunately, it's very computationally efficient to draw samples inside such a convex hull as this one, and therefore we can obtain a lot of samples very fast. What we have been interested in this work is to look at solutions that are different in terms of their technology mix implemented. We did that by allowing the near-optimal solutions to deviate with 10% from the optimum in terms of total system cost, and we then used the mapping all alternatives method to sample 500,000 of these near-optimal model solutions. If we plot the installed wind turbine capacity against the installed solar PV capacity of the entire model, we get this figure here. So first you'll see the two marginal distributions, and then we have this blue cloud representing all of these 500,000 samples. So where the cloud is very dark blue, the samples are very densely located, and where the cloud is more lighter blue, the samples are a bit more sparsely located. You'll see that the solar PV and the wind turbine capacity are negatively correlated. That is because the model can either choose to use solar PV or wind turbine capacity to decarbonize the energy supply. It will rarely use both of the technologies in large quantities at the same time. On our figure, we have also shown 4 scenarios. These are the model optimum, the high equality, a scenario that overperforms on CO2 reductions, and a scenario with a very large wind turbine capacity. These scenarios are seen here. So in the model optimum, we see a good mix of technologies used across Europe, and we see a very strong transmission grid. In the high equality scenario, we see a much weaker transmission grid, and we see that technology capacities has been relocated to be in the countries that also has a very high energy demand. In the large wind capacity scenario, we see that there's of course a lot of wind turbine capacity in Northern Europe, combined with a very strong transmission grid. And in the low CO2 emission scenario, we see that the model installs more storage technologies than we've seen in the other scenarios, combined with a very strong transmission grid. In this figure I have included a bit more data. So first of all, you'll see the installed capacity of the two storage technologies. Then we have the installed capacity of the solar PV, wind turbines, and the gas turbine capacity. Then we also have included a measure of the equality in the model. Here I've used the Gini coefficient. A low Gini coefficient represents a scenario with a very high equality, whereas a high Gini coefficient represents a scenario with a very high inequality. I have also included the CO2 reductions relative to 1990 levels and the cost increase relative to the cost optimal solution of the model. You will see that all of these variables are found once here on the y-axis and once on the x-axis. Some of the findings that we did here is that we see a very large variation in the model solutions at only small increases in total system cost. Remember that all of these scenarios only have a cost increase of a maximum of 10% relative to the cost optimal solution. So you see here that in one extreme we have scenarios with almost no installed solar PV capacity, and in the other extreme we have scenarios with more than 2000 gigawatts of installed solar PV capacity. Some of the other findings that we also did is that we see a very strong negative correlation between the gas turbine capacity and hydrogen storage. That is because these two technologies fulfill the same role in our model. So they both provide energy when renewable resources are scarce. We also see a very high or very strong correlation between equality in the model and the installed solar PV capacity. So you see down here we have the Gini coefficient, and when we have a low Gini coefficient, we also see a high installation of solar PV capacity. We also find a strong correlation between solar PV and battery capacity. And to give an example of how you can use this figure, I have introduced here a scenario with a very high installation of solar PV capacity. So let's say that we are going for a scenario with a high solar PV capacity. Then we can read where this red line intersects with the blue clouds, how much capacity we need of the other technologies. So for example, we see that if we want a very high level of solar PV capacity, we only need a little or a small amount of wind turbine capacity, and we can do so for all the other values as well. So in order to conclude on this work, we can say that we have indeed been able to identify all of these near optimal model solutions, and it is also very relevant to look at this because you can actually achieve some solutions with very different qualities than the cost optimum and only small increases in total system cost. That was it for me. Thank you for your time.